Section 11.3 is probability of multiple events. I can find the probability of event A and B, and I can find the probability of event A or B. Those are our learning targets and what we're shooting for in this section. Big idea here. To find the probability of two events occurring together, it is necessary to determine whether the occurrence of one event affects the probability that the other event will occur. When the occurrence of one event affects how a second event can occur, the events are dependent events. One depends on the other. Whatever happens first changes the possibilities for the second. If the occurrence of one event does not affect the second event, these events are independent. So in example 1 here, we're just going to be classifying events. Are the outcomes of each trial dependent or independent events? So in an A, if we roll a number cube and then spin a spinner, rolling a number cube has absolutely nothing to do with a spinner. We can roll a number cube, get anything 1 through 6. We can spin our spinner, get any number on there. They have nothing to do with each other. So these are going to be completely independent. For part B, though, it says pick one flashcard and then another from a stack of 30 flashcards. Okay, here these are dependent because when we pick a flashcard from a stack and then pull another one from it, we can't pick the same one that we already picked. So that one is out of our possibility now. Now we only have 29 cards to pick from. Picking the first flashcard changed the second group that we can pick from. So these are dependent. The second group that we can pick from and our options there depend on which flashcard got drawn first. Take a second to think about these. Now you select a coin at random from your pocket. You replace the coin and select again. Are your selections independent events? And explain. Okay, we picked a coin from our pocket, and then we put the coin back and picked again. So these are going to be independent because we put it back. So we have the exact same starting point for both times. The first time where we grabbed a coin, figure out what it was, wrote it down, whatever, put it back, and now we have the exact same sample space. So we can pick any of the same options. It didn't change. So even though we're using the same coins, okay, nothing actually changed. It's just the same thing again because we put the coin back. So these are independent events. Take note here on page 688, the probability of A and B. If A and B are independent events, then the probability of A and B is the probability of A times the probability of B. And that's just our counting principle. It says that we can multiply the two. So at a picnic table, there are 10 diet drinks and 5 regular drinks. There are also 8 bags of fat-free chips and 12 bags of regular chips. If you grab a drink and a bag of chips without looking, what is the probability that you get a diet drink and a fat-free chips? So our probability, remember, is our outcomes we're looking for, so what we want, divided by our total outcomes, our total possibilities. So when we look here, we are looking for a diet drink, first of all. We have 10 diet drinks. How many total drinks do we have? Okay, we're not comparing diet to regular, we're comparing diet to the total amount of drinks. So we have 10 and 5. So our total possibilities is 15. I can simplify that to 2 out of 3. Don't have to, but you can. We're going to multiply here because we want a diet drink and fat-free chips. So we're going to take our probability of A times our probability of B. And again, that goes back to our counting principle from the first section. Our probability of B. Again, it's what we want. We're looking for fat-free chips, which has 8 bags. And then we're looking for the total chips. So there's 8 fat-free and 12 regular. We add those to get our total, and there's 20 total. And again, I can simplify that to be 2/5. Going back to chapter 8 with fractions, when I multiply fractions, I multiply straight across. And I get 4 out of 15. As a decimal, that's going to be approximately 0.26 repeating, or 267 as a decimal. That's my probability. And as a percent, then it's about 26.7%. So there's a 26.7% chance that at random, if you're not looking, you'll get a diet drink and fat-free chips. Now, in the last example, we want to know what is the probability that you get a regular drink and regular chips. So if we look back here, regular drinks were 5, regular chips were 12. So our probability of regular drink times our probability of regular chips. Regular drink we said was 5. There were 15 total. Regular chips we said was 12, and there were 20 total. Again, we can go ahead and simplify this. 1/3 times 12 over 20. We can take a 4 out and get 3 over 5. Again, we multiply across, or we can cancel. And I'm going to get 1/5. If I multiplied across, I'd have gotten 3 over 15, which simplifies to 1/5. So either way, as a decimal, my probability is 0.2, or I can write it as a percent as 20%. So there's a 20% chance that we would get a regular drink and regular chips. So even though our odds of getting regular chips are better, they are not better of getting a regular drink. So the two combined is actually a smaller probability. Two events that cannot happen at the same time are mutually exclusive events. If A and B are mutually exclusive events, then the probability of A and B is going to be 0. So, mutually exclusive events here. We roll a standard number cube. We have to determine, are these events mutually exclusive? If we roll 1 die, can we roll a 2 and a 3? No. So, are these mutually exclusive? Is our question? Yeah, they are mutually exclusive. We can roll a 2 or a 3, but we cannot roll both. Okay, if we only have 1 die to roll, we can only roll 1 number. We cannot roll both. So you can explain that however you want. Okay, as long as it fits our description. So rolling an even number and a multiple of 3. Is this mutually exclusive? It's not mutually exclusive. We can roll a 6, for example. 6 is both even and a multiple of 3. So it is not mutually exclusive because there is something that fits both those categories, a 6. Now, you roll a standard number cube. Are the events mutually exclusive? Explain. Rolling an even number and rolling a prime number. Is that something we can do? Can we roll both an even number and a prime number? Yep, we can roll a 2, for example. So are these mutually exclusive? No, not mutually exclusive, because there is something that works. Mutually exclusive means that they don't work with each other. There's no options that work for both. Here, 2 does. It's prime and even. It's actually the only even prime number. Rolling an even number and rolling a number less than 2. Can we do both of those things? We can't, so it's mutually exclusive. One excludes the other. We cannot have both. The only numbers less than 2 that we could roll is 1, and 1 is not even. So it's mutually exclusive because the only options exclude each other. I'm going to stop this one here and finish on the next one.